Hi. Let's now take a look at ideal gas. For ideal gas, there are 4 sets of formula. So the first set of formula, we're going to show you how it is actually being derived. So we're going to start off whereby we actually have a cubic space, right? Length is L, and you actually have got n ideal gas molecule inside them, all right? You're going to study a single gas molecule that's moving towards this shaded wall. So as a result of moving and colliding on the wall, it actually creates a change in momentum. And from the change in momentum, it actually exerts a force on the wall. So a couple of assumptions to take note. The first assumption is clearly that when the ideal gas molecule hit the wall, it hits the wall perpendicularly, which means that if this was the wall, the molecule will collide it, and just before it collides, its momentum is mu, and after colliding, it will depart with a momentum mu, but in the opposite direction. So the first assumption is that the collision on the wall has to be perpendicular. The second part is that the collision on the wall is deemed to be elastic, which means that as you evidently see that the energy, the kinetic energy of the molecule does not change. Finally, the gas molecules must obey Newton's law of motion, which is F equal to ma, because that's the equation we're going to use to derive the force exerted on the wall. So with that, let's take a look at what is the force that is actually exerted on the wall as a consequence of a single gas molecule for a single collision on the wall. So so as illustrated earlier, the change in momentum will be 2mu. It takes place over a short period of time, delta t. So during this delta t, we also need to take note that the gas molecule is moving very fast, so it could actually hit the wall a couple of times. So the number of collisions on the wall during this duration of delta t will be the distance traveled by the gas molecule divided by 2L. So that will give you a good gauge of the number of collisions. So U multiplied by delta t is actually the distance that is being traveled by the gas molecule. So you divide by 2L. That's how we derive the number of collisions that's going to hit on the wall by a single molecule. So with that, the force exerted by the single molecule on the wall will be actually F multiplied by N, and we end up with mu squared over L. For this modeling with N gaseous molecule, you realize that 1/3 of them could be estimated to be moving in the Z direction, 1/3 moving in the X direction, another 1/3 moving in the Y direction. So therefore, because of that, the total force exerted by N molecules on a single wall, on a shaded wall, will be 1/3 N multiplied by the mu squared over L. That means you have now 1/3 number of the gaseous molecule that will be hitting on the wall, and each of them will give rise to a force of mu squared over L. So this is actually the total force exerted by N gaseous molecule. If using this expression, we can now take the total force and divide by the area to give you the pressure exerted on the wall. So with that, L multiplied by A essentially will give you the volume. So V is actually the volume, all right? And finally, you will find that as far as for U squared is concerned, obviously all the gaseous molecules are not all going to be moving at the same speed, because at a specific temperature, there will be a range of speed for the gas molecules, as shown inside here by the Boltzmann distribution graph. This graph tells you that at a certain temperature T, you will have some molecules, a certain number of molecules with a speed C1 and a certain molecules with a speed C2. Okay, so the best representation for all these possible speed is to make use of root mean square speed. All right, so C represents the root mean square speed, which means C squared actually represents the mean square speed. So that's a representation for it. So we could replace the U squared with this. So here you go. This is the first set of formula you need to know. And this set of formula is given to you in the data booklet. Okay. The other set of formula that you need will be PV equal to nRT. The P and V is exactly identical as the one ahead, which is your pressure and your volume. Your T is your temperature in Kelvin. And your R is your ideal gas constant, fixed at 8.31 joule per Kelvin per mole. And N is your number of mole. All right. So the difference between these two formula is that one is actually relating it to temperature. So the other one is relating PV to speed. and the mass of individual gas molecule, and N is the number of gas molecules. With these two formulae, let's derive the third one. To derive the third one, these three are the data booklet values that we listed off. K is the Boltzmann distribution, Na is your Avogadro's constant, R is your ideal gas constant. One of the things that you need to realize is that the Boltzmann constant is actually R divided by Na. So with that in mind, R is equal to Na to K, which means this R here, I can now replace it with NaK, all right? And the N multiplied by Na, N is the number of moles. So assuming 1 mole of gas, and Na is Avogadro's constant. So the product of the number of moles and the Avogadro's constant, you are actually getting the total number of gaseous molecule. So you will get PV equal to NKT, all right? So sometimes for equation number 2, we will say that students also need to remember a variant of the second set of formula, which is PV equal to NKT, all right? And clearly for us equating this and this, which is actually the two formula here, your PV and PV and N can actually cancel away, and you can establish a relationship whereby 1/3 M mean square speed equal to KT. Once we have that, we know that we can determine the average of the kinetic energy of an ideal gas molecule, which is half mc squared, and that will be equal to 3/2 kT. In summary, one need to bear in mind, therefore, from this formula, that the average Ke of a molecule depends on the temperature, okay? And the total kinetic energy of the gas sample can now be equal to 3/2 nKT. Finally, for our last set of formula, we could also express PV equal nRT, whereby the number of moles can be expressed as mass divided by molar mass. What is molar mass? Molar mass is the mass of per unit mole of gas. So the if you take the mass of a sample divided by MR, that will be to give you the number of moles. We could also calculate the total mass of a gas sample by simply multiplying the number of a gas molecule multiplied by the mass of each molecule. So with this expression and comparing it to equation 1, all right, which is 1/3 nmc squared, we could now actually make these two equate together, and we'll end up with 1/3 of mean square speed equal to RT divided by the molar mass, and from there your root mean square speed of your gas molecule could be determined by this expression. This is the last formula. In using this formula for calculations, be mindful that the MR is in kilogram per mole. Thank you.